Okay, in this video we're going to talk about the concept called the reaction quotient. So we can calculate the ratio of the concentrations of the reactants and products whether they're at equilibrium or not. Now, we only call the ratio the equilibrium constant when the reaction is actually at equilibrium. If we're not at equilibrium, then instead of calling it the equilibrium constant, because we're not at equilibrium, we call it the reaction quotient. And instead of using the letter K, we use the letter Q. But the form of Q is identical to K. So if I gave you this generic reaction and said write the equilibrium constant expression, or write the expression for the reaction quotient, we would write the same thing. Right? So QC, if we're talking about concentrations, would be the concentration of C raised to the C power, the concentration of D raised to the D power, the concentration of A to the A, and B to the B. So exactly the same thing we would have written for the equilibrium constant expression, right? The difference is, when we're not at equilibrium, we call it Q, the reaction quotient. If we know we are at equilibrium, then we call it K, the equilibrium constant. And so what we can use the reaction quotient for is to determine in which direction does the reaction need to go to get to equilibrium. If we calculate Q and it's equal to the value that K has, then we know we're at equilibrium. So let's look at that. How can we use the reaction quotient to predict reaction direction? So the way I think about it is I just use the idea in general, right? Q, or K, is the products over the reactants. And so what we're representing on the chart here is for some generic reaction, we're told that the equilibrium constant is 1.45. And so wherever I'm at in terms of my ratios of products and reactants, we're always trying to get to, in this case, 1.45, right? But all reactions are trying to get to equilibrium. And so what this blue line represents is the ratio of products to reactants. So this is essentially either the reaction quotient or the equilibrium constant if we happen to be at equilibrium, right? And in this case we have all reactants. In this case we have all products. And so as we make more products and less reactants, the value of the reaction quotient increases. And so if we're in this situation where Q is less than K, right, the way I think about that is that Q is too small. I don't have enough products. And so in that case, the reaction has to go to the right. In other words, we're going from A to B, right? So we're saying the reaction goes to the right to make more products in order to get to equilibrium. Right, so when Q is less than, say, I say, okay, Q is too small. The reaction goes to the right. And when we say to the right, right, the products are on the right, we're saying that the reaction is going to make more products. If we're in this scenario, right, where now Q is bigger than K, right, so Q is too big. In my head, that means if Q is too big, I have too many products. And so in that case, the reaction needs to go to the left. I need to, right, the reactants are on the left. I need to make more reactants. I need to make Q smaller to get to equilibrium. Right, so when we say the reaction goes to the left, it means we're going to be converting products into reactants. Now another way to help remember these, and this only works when you do the lesser than greater than comparison. If you write Q on the left and K on the right, but if you think about the cartoon Pac-Man, right? When Q is too small, waka 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 waka, right? Pac-Man's going to the right. The reaction goes to the right. If Q is bigger than K, right? Waka 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 waka. Pac-Man's going to the left. The reaction goes to the left. All right, but that trick only works if you write Q on the left and K on the right. Or the way I remember it is if Q is too small, I don't have enough products. The reaction needs to go to the right to make more products. Or if Q is too big, right, that means I have too many products. The reaction needs to go to the left to convert some of those products into reactants. Okay, so here's an example of how we would use the reaction quotient to determine in which direction the reaction must proceed to get to equilibrium. So we're given a chemical reaction, we're told the equilibrium constant, and we're given some pressures. In this case, we have a Kp, so we're working in atmospheres as opposed to molarity. And we want to know in which direction the reaction will proceed to reach equilibrium. So when I want to know which direction a reaction is going to go, I need to calculate Q, and then I'll compare that to K. So the expression for Q, because we're dealing with pressures, instead of using the notation for concentrations, I'll use the notation for partial pressures. So the pressure of NO squared divided by the pressure of N2 times the pressure of O2. And so if I go ahead and plug in the values for the pressures I was given, I have 10.0 squared over 5 atmospheres times 5 atmospheres. And so I get 100 over 25, or my Q is 4. Alright, and so in this case, my Q is 4, my Kp is 5, so in this case, Q is bigger than K, right? I have 4.0 versus 0.05, right? So in this case, Q is too big. I have too many products, so the reaction needs to go to the left, right? So I'm going to be converting NO into the reactants in order to get to equilibrium, right? Or I could use Pac-Man, right? Pac-Man's going to the left. That tells me, again, the reaction needs to go to the left to get to equilibrium. I need to convert the products into reactants to get to equilibrium.